Okay, so let's continue. Yesterday we just covered several types of capacitor. So it includes the parallel plate capacitor, uh, cylindrical capacitor, and also spherical capacitor. So three types of capacitor, which is easier to derive the capacitance. So uh, it covers the equation. Why it look like this? Why it look like this? Actually, this one you can use the Gauss law to derive it easily. Oh, not it would be quite similar to this. Just 3 volts. You can derive it. So let's consider a sample problem. So here you can see here there is a simple circuit, a battery, a switch, and a capacitor. Well, so the switch is closed to connect the uncharged capacitor of a capacitance C equals 0.25 microfarad. Yeah, actually the SI unit for the capacitance is farad, and I suppose most of you should already know it. To the battery of the potential difference, V equals 12 volt. The lower capacitor plate has a thickness L equals 0.5 centimeter, and the phase are this is the surface area, the area of the capacitor, and it consists of copper, in which the density of the conduction electron is N. Electrons per meters cube. From what depth d within the plate must electrons move to the plate place as the capacitor become charged. So it tells you that well, actually, ideally all the electron must be lie on the surface of the metal, but actually it's not possible to be infinite density. So there should be some thickness, but this thickness is quite small. So here we need to calculate what is the thickness of the electron here within the metal, given this voltage, capacitance, and thickness of the plate, so on and so on. So for capacitor, as you can see, we have C and V, so you can simply calculate the charge. Q equals ZV, and you just plug in 0.25 mu, which is 10 to the minus 6, and V is 12. So Q is 3 microcoulomb. So that's the total amount of charge on this plate. So you can consider this orange part. You can consider there are some electron. Some electron are there, and these are there are no charge at this part. So it tells you that the density can be as high as this one. It means that there are totally 8.49 times 10 to 28th power electrons within a meters cube. So it cannot be more dense than this. So N, the capital N, would be 3 times 10 to 6 over 1.6 times 10 to minus 19. So this one is the elementary charge amount. So if we divide Q by the elementary charge amount so that we can know that there are 1.87 times 10 to 13 electron. So you just divide it. So it is pretty easy. You just divide the charge, the Q, by the elementary charge so that you can know the number of electrons. So we can imagine n times the area times the thickness would be the total amount of the electrons, total number of electrons. So this is the density, the volume density, and is the volume density because it's over meters cube. So you multiply by the volume, as you assume the electrons are distributed uniformly, so that you multiply the density by the volume, so that it is the total number of electrons. So finally, we have B equals N over A small n. So you plug in 1.87 times 10 to 13 over A is this one, 2 times 10 to minus 4, 2 times 10 to minus 4, and then n is 8.49 times 10 to 28. So finally, A should be 1.1 times 10 to minus 12 meters. So it's very thin, It should be 1.1 picometer. You can imagine what is picometer, because usually you know what is nanometer, because recently many news about the chips technology. So you hear something like 5 nanometer process, something like that. So it's about the transistor. Actually, for the most advanced technology, it's not really like that. But for the older technology, like 0.18 micrometer, which is actually 180 nanometer, then usually you learn the most transistors in maybe applied electronics. So you have this is called the gate. You have the drain, source, something like that. And actually this maybe this 180 nanometer means this length is 100 nanometer. And I think recently we are using a 28 nanometer process. So actually this one can be as short as 28 nanometer. 21 nanometer means 10 to minus 9 meter, which means 1/1 billion， 就是11分之1米，就是把1米分成11份，就是1个 nanometer， 大概是这个意思。
What is the diameter of city?
Huh?
What is the diameter of city?
What is that? What?
会元素的直径有多少？
你查一下那个表，我怎么知道会元素？半径应该落在 N 等级啦，就是就是如果到很低几个纳米那种的话，可能那个 channel length 只有几个原子吧。好，那38章的时候我们会学到那个 quantum mechanics 啊，我会提到那个 tunneling effect， 所以这跟那个有关的，这个是电子可以穿肠的那个故事，就是很特幻的故事啊，到时候会提到。So next page, yeah, we have capacitor in parallel and in series. So I suppose most of you are ECE students, so you should know how to calculate parallel capacitor or series capacitor. So it is in the reverse case as the resistance, parallel resistance, because when you have series resistor, you add them together. But here you have parallel capacitor, you add all of them together. So for parallel capacitor, you add all of them together. So this one is parallel. This one is parallel capacitor. So you just use the conservation of charge. So if you have one capacitor, then you have charge like this, and then as long as they are in parallel, so that they share the same V. So in this case, we have Q1 equals Z1V, Q2 equals Z2V, Q3 equals Z3V. And then after they parallel, the charge are shared because the charge are conserved. The charges is conserved. So the total Q is Q1 plus Q2 plus Q3. And the voltage shouldn't change. So in this case, C equivalent is nothing but C1 plus C2 plus C3. So it's very trivial. And for series capacitor, you connect back to back. Cannot connect the capacitor back to back. So actually, in this case, we have plus Q minus Q plus Q minus Q plus Q minus Q, which means that within the middle parts, we have negative Q on this plate and plus Q on this plate. So this is electrically neutral, and so as this one. So they share the same Q. Rather than this one, they share the same V. So in this case, we have V1, V2, V3, V1, V2, V3. So the total V should be V1 plus V2 plus V3. So the total V, the battery have a potential V. So the voltage drop for different capacitor V1, V2, V3. So we have V equals V1 plus V2 plus V3. Yeah. So using the same formula, we have V1 equals Q over C1. But here, Q is the variable to share. As I mentioned here. So we have V1 equals Q1 over C1, V2 over equals Q over C2, V3 equals Q over C3. Something like this. So as we have V equals V1 plus V2 plus V3, and then we just substitute here, and then we find that 1 over C equivalent equals 1 over C1 plus 1 over C2 plus 1 over C3. So which means that CQ over 1, C equivalent equals 1 over this stuff, this quantity. So this is the opposite as a resistor in parallel or in series. So any questions? No questions. Very easy. So next we consider energy stored in the electric field. So it would be quite easy, I think. So for the conclusion, it is nothing but 1/2 CV squared, 1/2 CV squared. So actually we use the simple integration, u equals integration of du, and then you consider at the very beginning the capacitor has no charge, and then you try to put more and more charge on the plate. Try to put some charge on the plate, and of course one positive and then another negative. So at the very beginning, you don't at the very beginning, the work done you need to put on it would be I think smaller. I think smaller because there are no charge on it, so you can put it easy. Then the work done will be varying after you put more and more charges. So actually, we just integrate v dq. Actually, du is v dq prime, vdq prime. And all we need to do is we try to put some charge on the plate until there are total q charges. So v is actually q prime over c. Finally, there will be q prime, or at any moment it will be q prime, and the voltage here would be q prime over c in the intermediate stage. So you integrate this stuff, and then c is a constant to factor out, and then you integrate q prime dq, which is nothing but 1/2 q prime square, and then you substitute. Evaluate at the q and 0 and subtract them. So it turns out to be q squared over 2c. And if you just plug in q equals cv, which means that q squared equals c squared v squared. So you just cancel 1 over c, so it will become 1/2 cv squared. Or if you just so this is another value which is called the energy density. Energy density small u, which is the u divided by the volume, which is AD. You may consider it is a parallel plate capacitor, so that C is actually epsilon naught A over D. So you just divide the AD, and then it will become epsilon E squared. Also, you need to substitute V equals ED. So it become like this. And maybe we'll not use it frequently. We'll definitely not use it frequently, but maybe we will see it again in chapter 33. But actually, it's just a formula for the physician. I seldom use this one. This one may be more useful. This one will be useful for an engineer, because because maybe you will consider the digital circuit, and maybe you have a inverter, and then you use a clock. To drive it. Maybe the clock is F. So the power consumption for this one would be something like this one is C load and C load. So the power consumption for this inverter will be P equals F CV squared, something like this. Because if you have a clock, you have the charging and the discharging. So you have 1/2 CV, and then the other 1/2 CV squared. 1/2 CV squared, 1/2 CV squared, and then totally it will become CV squared. And then in a second there will be f time. This is the frequency f hertz. So you multiply the energy by the f, so that it becomes the power. Maybe you will see it in later course. I don't know. So we have another sample problem. So an isolated conducting sphere whose radius is r, r is 6.85 centimeter, has a charge q. How much potential energy is stored in the electric field? Potential energy stored in the electric field of charged conductor. What is the energy density at the surface of the sphere? So it will be very easy. Just plug in the value and then you get the result. Okay, so actually we have a conducting sphere, which means that we should use the formula C equals 4 pi epsilon naught r. You can still remember, but actually you don't really need to remember. We just talked about it yesterday. And so U is nothing but Q squared over 2C, Q squared over 2C. And we can just plug in this one to here, so that it will become Q squared over 8 pi epsilon naught, epsilon naught r. So it will be nothing but 8.99 times 10 to 9, which is k, which is 1 over 4 pi epsilon naught. And then we multiply it by 1.25 times 10 to minus 9 square, which is q square. And then we have 2r. R is 6.85 centimeters, so it is 0.0685. So the answer will be 1.03 times 10 to minus 7 joule. So for B, if you use actually, if you use U, small u to be U over 4 pi r squared, which is the volume of the sphere, then it will be incorrect. Actually, it's the surface area, not this one. So it shouldn't be like this, because the energy stored in a spherical capacitor is not uniform. For parallel plate capacitor, the E field is uniform, so the energy is also uniform. But here, for a capacitor, for the spherical capacitor, it is not uniform, so that you cannot use the total energy stored divided by the volume. It's not correct. So we need to consider. E equals 1 over 4 pi epsilon naught times Q over r squared. Q, Q. So the total, so the U is 1/2 1/2 epsilon naught E square, and then we just substitute it there. So it will become Q square over 32 pi square epsilon naught R to the 4th power. So finally, we just plug in the values 1.25 times 10 to times 10 to minus 9 square, and then over 32 pi square. Epsilon naught is 8.85 times 10 to minus 12, and then R is 0.0685 to the 4th power. So it becomes a value to be 25.4 micro joule per meter cube. Okay, so next we consider capacitor with a dielectric. We consider inductor, capacitor with a dielectric. So before I mentioned that no matter what is the three structure, no matter it's a parallel plate capacitor, cylindrical capacitor, or spherical capacitor, you either increase the size or either making two plates close to each other, then you can have a larger capacitor. So here there's another trick. You can place something inside the capacitor, which makes it look like a sandwich. So, and then the capacitance will become larger. So if we place, if the space between the plate of a capacitor is completely filled by a dielectric material, the capacitor C in vacuum 真空的，跟有空气是一样的，对电的特性来说，真空跟有空气是一样的。So the capacitance C in vacuum is multiplied by the material dielectric constant. So we define another physical variable called the dielectric constant, which is a Greek letter called kappa. It's not K, it's kappa. So which is a number greater than 1. You all, as I already showed, you always face the kappa to be greater than 1. So it will look like this in a region completely filled by a dielectric material of dielectric constant kappa of the electrostatic equation contain the permittivity constant epsilon naught are to be modified by replacing epsilon naught with kappa epsilon naught. So it will be easy. All the equation you can reuse if all the air gap is filled by the dielectric. You just need to replace epsilon naught by kappa epsilon naught, or you just add the kappa before the epsilon naught, then it will be fine. So it means that here we have a battery. Of course, with a potential V, electric potential V. So at the beginning, there will be some charges stored in this capacitor, and then you try to plug in the dielectric slab between the capacitor. then now you can see that there are more charges. There are more charges stored here at this capacitor. And at this case, the voltage remains the same. But if the charge become more, so you can imagine the capacitance become larger because it is something like Q equals CV. Q equals CV. So V is unchanged. Now for the left case, Q is smaller. So C is smaller. So for the right case, Q becomes larger. So C becomes larger. So this is the effect when you just plug in the dielectric slab between the capacitor to replace the air or the vacuum. Or in another case, you just store some charges. You just store some charges there, and then you disconnect the battery so that the charge cannot go away. So it remains the same charges for both cases. And then you try to measure the voltage across the capacitor. So after you plug in the dielectric slab, the voltage will drop. The voltage will drop. So you can use the similar formula. Actually, you can. So because Q is constant, yeah. Actually, you can see it like this. For this case, Q is constant because you just disconnect the capacitor. The charge cannot move. So Q is a constant here. So if the voltage is larger for the left side, C should be smaller. And for the right-hand side case, V becomes smaller, so that it tells you that the C becomes larger. So it is inversely proportional. So for this case, Q and C is proportional to each other. So any questions regarding to this one? Okay, so let's talk about some hardcore physics. It is quite difficult to imagine, but you can just regard it as a story. It doesn't really that important to understand this stuff for the next part. But if you like physics, you'll feel it is interesting. So it tells you that what is the really physics for this dielectric. We'll talk about dielectric, but what is it inside the dielectric? So it's just like there are many dipole inside the dielectric. So so for some case, the dipole will be something like they will orient to different direction. And if you apply an electric field, then they will more or less facing the same direction. If you don't really apply an electric field to it, then it will facing random direction. You can imagine a case if I just said, let's have a break, then you may facing different direction, and then you may track with other student, or you may just walk out to take a rest. So it's just like this case, random orientation. But now we are having classes. So most of you will be facing the board, even if you are not listening. Actually, you generally facing the board, so it's just like the dielectric. I apply the electric field here, so you're facing this direction. You're not facing the backward, right? So you can imagine like this. So for non-polar dielectric, if we just the initial electric field inside the non-polar dielectric slab is 0. If you just don't apply any E field to the dielectric, it will facing random direction. So that, of course, as you have learned in previous chapter, you know that dielectric, or the dipole there should generate some E field, although it may be quite weak, but it will generate some E field. But as long as they are facing different direction, so that the E field will generally cancel each other out. So it's just like there are no E field inside the dielectric. And you can imagine, if you can really generate some electric, it needs some power to remain that stage. So it is not a natural way to have these cases. So it will generally have no electric field in the dielectric if you don't really apply an external electric field to it. So after you apply some electric field to it, then there will be something different. As I mentioned just now, they will generally facing the same direction, because you can imagine if you have an electric field pointing to the right side, so the positive charge which will want to go to the right side, and the negative charge will go to the left side, so that they will just align. Not necessarily as good as this one, but actually they will just align to this side. So the E field point to the right side, so the positive side for the dipole will also go to the same direction. So in this case, you can now ignore this one. So it generally the dipole itself will generate an other E field, because it will look like the average position for the positive charge will slightly move to the right, and the average position for the negative charge will slightly move to the left. So it feels like there are some positive charge here and some negative charge here. You can imagine like that. So it turns out it will generate another E field opposite to the external field, and then the overall E field within the dielectric will become smaller. Part of the electric field will be cancelled by the dielectric itself. So this one tells you that if you really want to generate E0, which is the external E field, then you have something like a parallel plate. This is positive charge, this is negative charge. So it will generate the E field pointing to the right side. And you can imagine the dipole will align in this direction, so that it will generate. So it is clear, because this is positive, this is negative, and for the dipoles, positive, negative. So it will have some E field or cancel part of the external E field. So it makes the overall E field in the dielectric to become smaller. So it's pretty interesting. So yeah. dielectric and Gauss law. So inserting a dielectric into a capacitor causes induced charge to appear on the faces of dielectric and weaken the electric field, as I mentioned in the previous page. Between the plate, the induced charge is then free of charge on the plate. So actually, just now we mentioned that if we use the capacitor with dielectric, then we just replace epsilon naught by kappa epsilon naught. So as the Gauss law, we can just replace epsilon by kappa epsilon. But it tells you that it plugs the kappa inside the integration. It tells you that the kappa may not be a uniform one. You can place two different dielectric in the parallel plate capacitor, and then it will feel like maybe there are some parallel or series effect. You may see some selective problems like that. So it just tells you that he tried to put the kappa in the integration to emphasize that kappa may not be a constant, but it doesn't necessarily that you can use hand calculation. Usually it's uniform, then you can use calculation. You just separate into several pieces, and then you can calculate it out. If it is continuously varying, then you need to use some really integration or some computer to calculate the results. So here it defines another variable called the electric displacement. D is a vector which is proportional to the electric field, which is D equals epsilon naught kappa E. So it is just a constant. Is another vector proportional to the E field. So in some textbook, it may write it as epsilon to be kappa epsilon, or there are many different notations, but some books to make it more better looking. So it will be something like this, and some book maybe just written as epsilon, like this. So if you just see different sources, maybe Wikipedia or something other textbook, then you will see quite a lot of different notation. So I just let you know, but actually in this textbook it just use D equals epsilon naught K kappa E. But actually D doesn't really appear later on, so you can just have some knowledge about it, and it's just fine. So here we have a sample problem, a parallel plate capacitor whose capacitance is C, which is charged by a battery with a potential V. The charging battery is now disconnected, and porcelain slab, copper equals 6.5 is slipped between the plate. What is the potential energy of the capacitor before the slab is inserted? Yeah. So okay. So what is the potential energy before it is inserted? So it is. So we have U initial to be 1/2 CV squared, 1/2 CV squared. So you just need to plug in C equals to 13.5 times 10 to minus 12. And then V is 12.5 square. So the initial energy is 1.055 times 10 to minus 9 joule. So this is the case before you put in the dielectric slab. So this is before. So what is the potential energy of the capacitor slab device after the slab is inserted? So here C prime will become 6.5, which is actually copper C, because you can imagine you just replace epsilon naught to be copper epsilon naught, and no matter which one it is, parallel plate capacitor or this one. So it is all of them are proportional to epsilon naught. All of them are proportional to epsilon naught. Or for parallel plate capacitor. For parallel plate capacitor, all of them are proportional to the epsilon naught. So if you just replace epsilon naught to be copper epsilon naught, so C will become copper times larger. So it is 6.5 C, which is nothing but we don't calculate it here. So UF is Q square over 2C. Q square over 2C. Yeah, because in this case, it tells you that the charging battery is now disconnected. So the charge is remaining the same, but the voltage will change. So if you use a 1/2 C prime V square, then you get the wrong answer because the voltage should have changed. So here Q would be 13.5 times 10 to minus 12 times 12.5, which is the original charge and the charge for this moment. It doesn't change. So over 2C prime. So 2 times 6.5 times 13.5 times 10 to minus 12. So it will become 1.62 times 10 to minus 10 joule. So the energy stored there will become smaller. So just now is 1 point something times 10 to minus 9. So now becomes actually 6.5 times smaller. So where is the energy goes to? Actually, you can imagine W equals UI minus UF. So it will become, you just plug in 1.055 times 10 to minus 9, and then minus 1.62 times 10 to minus 10. It will become 8.93. 8.93 times 10 to minus 10 joule. So this is the missing energy. So because it tells you that the slab is slip between the plate, which means that you don't really put it inside the parallel plate. It's somehow like you just put the slab close to this one, and then it slip inside. So the energy is used to attract this slab into here, so that the total energy becomes smaller, because the energy loss is stored in the dielectric itself. Or you can imagine, just now I mentioned that if you apply an external E field to the dielectric, then the dipoles inside the dielectric will align to the same direction, so that the energy is stored here. So most of the energy is stored in the dielectric itself. Okay, let's finish the final example, because this is the final one. I don't want to cut it into many parts for the recording. So here we have another sample problem. So a parallel plate capacitor with an area capital A and a separation D. A potential difference V0 is applied between the plate. So this is, maybe you can consider this is 0 volt, this is V0 volt. So the battery is then disconnected, and the dielectric slab of thickness B, which is smaller than D. So you can consider B is this one, this orange one is the dielectric slab, which is smaller than the separation of the capacitor D. And the dielectric constant copper is placed between the plates, assuming that A is blah blah blah, D is blah blah blah, V0, B copper. What is the capacitance C0 before the dielectric slab is insert? So it would be quite easy, because it's a simple parallel plate capacitor. So it is nothing but C equals epsilon naught A over D, and then it is 8.85 times 10 to minus 12, and then it is 115 centimeter square, but we need to convert it back to meter square. So it will become 115 times 10 to minus 4, because when you convert centimeter to meter, it is 10 to minus 2, but here it is centimeter square, so it will transform to meter square. It should be 10 to minus 2, and then square, so it will 10 to minus 4. And then over D is 0.0124. So this is 8.21 picofarad. So this is easy. So the next one, what free charges appear on the plate? So it asks you about the Q0. Before you put in this lab, there should be some Q or Q0. Actually, Q is the same as Q0. I think. Yeah, not necessarily Q0. Yeah, you can just consider this Q is Q. So actually Q here I make it Q0, but it's fine. So we can have Q0 equals Z0 V0 V0. I think there will not be another Q. So you can just make it Q is fine. Because this is Q, this is minus Q. So I can just make it Q is good enough. So C0 is 8.21 times 10 to minus 12. And then V0 is 85.5 volt. So Q will become 7.0 Q times 10 to minus 10 Coulomb. So it's still very easy. Still very easy. So 7.02 times 10 to minus 10. So you can write it as 702 picocoulomb. Yeah, it's actually the same. So for part C, what is the electric field E0 in the gap between the plate and the dielectric slab? So actually before the dielectric slab plug in, it should be E field. It should be an E field. And after you plug in the slab, but outside the dielectric, there should also be the same E0, because the dielectric itself only generate the E field inside it, but it will not generate the E field outside. So it doesn't really change the E0 outside the dielectric. So it should be pointing this direction from the positive plate to the negative plate. So there should be E0 here, E0 here. So here we have epsilon naught integration of E dot dA equals Q. So we just let me see. We just consider this Gauss surface 1 for Gauss surface 1 So we have positive Q here. And then it should be nothing but E0A, because there will be no flux through the upper surface and the left and the right. So there is only E0A. So it should be epsilon naught times E0A equals Q. So E0 should be Q over epsilon naught A. So it will become 702 times 10 to minus 12 over 8.85 times 10 to minus 12 times this one, 115 times 10 to minus 4. So it will become 6900 volt per meter. So this is the E field in the gap between the plate and the dielectric slab. So after you plug in the slab, there should be some positive charge, something line on the bottom, and there's something negative charge line on the top. So there will be a E internal inside the dielectric to cancel part of the E0. Oh, actually, there will be E0. And then inside the dielectric, there will be another E field cancel part of the, maybe what we can call it E prime. So E1, which is the E field inside the dielectric, which will be E0 minus E prime. E prime is the E field generated by this dipole, and cancel parts of the E0. So it becomes E1. So you can regard it as there are some charges called Q prime here, which should be smaller than Q. Q prime should be smaller than Q. But actually, we don't really consider it in the Gauss law. So here, when we try to calculate E1, we consider the Gauss surface 2. So so it will become like this: epsilon naught integration of kappa E dot dA equals Q, or equals negative Q. Equals negative Q. Because if you just include this area, the total charge should be negative Q, and here. Or you can imagine it is somehow like there are. It is not necessarily there are some charge Q prime on the bottom plane, and Q prime negative Q prime at the top plane. It is somehow like this. It is somehow like there are many dipoles aligning like this. And so if you just include this part, so actually there are no net charges in this region. So we don't really consider a Q cross Q prime on the right side of the Gauss law. So for this case, there are no E field in this plate, so there are no contribution here, no contribution here. So there are only contribution for this one. But actually, the E1 should be pointing downward. Although there are some E prime pointing upward, but actually E prime should be less than E0. E1 should be less than E0. So E1 should still point to the lower direction, the bottom direction. So it makes this integration to be a negative value. So it will become negative epsilon naught kappa E1A. So the left side will look like this, and then the right side will be negative Q. So it turns out that E1 would be Q over epsilon naught kappa A. So we plug in the value. So it is 702 times 10 to minus 12, and then this is 8.85 times 10 to minus 12, and then kappa is 2.61, and then the area is 115 times 10 to minus 4. So the answer will be 26 4 voltage parameter. Ouch. So the E view will be much weaker inside the dielectric slab. So for the next case, we consider the potential difference between the plate after the slab has been introduced. Because as at the very beginning, V0 is 85.5 volt to charge this capacitor before the slab is plugged in, and then the battery is disconnected. So after you plug in the slab, the voltage will change, and it will become smaller, So we really need to calculate this final voltage. So actually, we can use the equation we have learned in the previous chapter. So here we have E0. We have E0 for the outside part, and we have E1 for the inside part. So if we integrate from the negative plate to the positive plate, so it will become E1 times B plus E0 times D minus B. Because over this path it is nothing but E1 has a thickness of B, so E1 times B, and for the remaining path, this part and this part would be D minus B for the air part. So we have E0 times D minus B. So it's somehow like adding them together, and actually it's just like a series capacitance. So we have 2640 as we calculate in the previous slide, and then B is 0.0078 meter, and then plus this is 6900 times D should be 0.0124. So V should be 52.3 volt. So the voltage potential, the electric potential becomes smaller between the plates. So it asks you what is the capacitance with the slab is in between is placed between the plates of the capacitor. So actually we can use C equals Q over V to calculate the new capacitance. So the Q doesn't change, so it is always 702 times 10 to minus 12, and then the new voltage is 52.3. So the final answer is 13.4 picofarad. So you can imagine this part become larger, and this part remain the same. This part remain the same. If this one is as big as this one, then you can imagine the capacitance is something like we can just recall C0, this one maybe we can call it Z0. C0 is 8.21 picofarad. So if this slab has a thickness of D, then you can imagine C would be copper, which is 2.61 times this one, which would be around 20 picofarad. But as long as this one is around half of it, a little bit more than half of the separation, so it just increase the capacitance from 8.21 to 13.4, not really to 20 picofarad.